Hello, welcome to Syntex Engine Dyno. Uh, reason we're making this video today is to try to explain the WinDyn Data Viewer and the data pack or data that you receive after having your engine dynoed here at Syntex Engine Dyno. Alright, when you get done with your dyno session, you'll be handed a CD that contains all the information on every pull, run, break-in sequence. Anytime that the engine was running, we were probably collecting data on it. So the first thing that you'll see is when you open it up is there's two screens. One is the graphic view here, and we'll talk about that probably on another later video. And the other is the first screen of the WinDyn Data Viewer, and that is here. As you can see, we'll go over these columns and what they mean, but this is the average data. Okay, it's averaged out at 100 RPM increments. Okay, the file will contain, you can look at this at different ways, but the file also contains the raw data. And let me see if I can show you what raw data looks like. Here we go. This is a data point. You'll see these lines are thicker. It's because if you zoom in here real quick, you'll see they're even thicker. But anyway, what you'll see here is you can see here this list is as page 1, and literally collecting data every RPM. Okay, sometimes 3 times in the 1 RPM, and you end up with 12 pages of data. Now this was a run that took almost 5 seconds. Okay, that is the reason, in order to make it easier to digest. Okay, we run with the average data here, which is once every 100 RPMs. Okay, as we talked about, the engine speed is located in the left-hand column. This pull was at 4,000 RPM to 6,600 RPM. It was done at 600 RPM per second. And this is the measure of the next column is engine power, horsepower. This is a measure that the dyno actually seen at that time on that particular day with those atmospheric conditions. Same with the engine torque, it was what was measured that day. The next column over is the O2 right-hand sensor and O2 left-hand sensor. On this particular engine, we had 2 O2 sensors located in the collector of each header. The air summary, standard cubic feet per minute. This was measured on an air turbine that went into the engine. You see them sitting on top of the carburetor, or in this case a Ron's toilet. And it measures the cubic feet per minute going into the engine. This brake specific air consumption, pounds of air per horsepower hour. All right. This is it measures the air by the weight, the pounds of air per each horsepower that it's made per hour. It's a calculated value, as you can see. This is brake specific fuel consumption, pounds per horsepower hour. This was a methanol fueled motor, and typically this is a measure of engine efficiency. Normally you'll see something 0.9 to 1.0, maybe 110, but an engine will become most efficient at its peak torque. And like I said, it was usually between 0.9 to 1.0 something, or there is where it should be. Again, this isn't an air-fuel ratio, this is just an efficiency ratio. To give you an example, like here it says 1.054 at 4,600 RPM. Well, if I added a water pump drive to it, okay, that number would change now to 1.082. So it's not a measure of air fuel. The air fuel didn't change, just the amount of horsepower that the dyno is seeing, because it took horsepower to run the water pump. So it's an excellent tuning tool as long as this number is going down and you're not losing engine torque. You're becoming more and more efficient. Volumetric efficiency. This is a calculated value, the amount of air going into the engine versus the size of the engine. As you can see, because of the tuning effect, it's easy to achieve over 100%. Alright, next screen. This is the corrected. We have our reference column, the engine RPM, and this is corrected horsepower. This is corrected to a standard. The standard happens to be the J607 standard. Alright, it's a way to be able to compare engines run, or the same engine run on different days, or actually on the same day. We've had the correction factor changing as the air heats up, so we can compare a run that we made at 8 in the morning versus one at 3 in the afternoon by comparing these numbers. Alright, so the J607 standard, just for reference, is 29.92 barometric pressure and 60 degrees Fahrenheit dry air. Again, this is corrected torque. Air fuel ratio. This is a calculated value measured in the pounds of air versus the pounds of fuel that was going into the engine. This is not an accurate value when you're doing a sweep test as fast as this engine was done, because this was going in a dragster type vehicle. It was accelerating at 600 RPMs per second, which was what the test was done at. This value lags behind on what the true value is. So, now if you were doing a step test or a steady state test where we just went to 4,000 RPM and held it there for 4 seconds, then went to 4,500 and held it there for 4 seconds, this number becomes very accurate. Fuel pressure. Again, we would do this doing EFI mapping is typically where we do stuff like that. Fuel pressure, mechanical fuel pressure, this is just measuring the pressure at the ejectors. Again, standard air, brake specific air consumption, brake specific fuel consumption, and again the volumetric efficiency. Screen 3 is again reference column on the left hand side. The oil pressure, why the engine was making its pull. Manifold pressure. This, although it's labeled manifold pressure, this was actually a vacuum pressure inside the oil pan, because this had a vacuum pump on it, and we were measuring what kind of engine vacuum it had. Battery voltage during the test. Specific power, horsepower per cubic inch. Again, a calculated value, the size of the engine versus divided by the horsepower. For a race engine, actually bigger is better, you know. Same with the torque. And the mechanical efficiency. Mechanical efficiency is it's a calculated value. Not too much. We don't pay much attention to this column for performance-oriented engines. But if we were doing fuel consumption type development, this is where we pay attention to the mechanical efficiency column. Brake mean effective pressure. All right. This is again is another calculated value. If you want to know how it's made, it can be made by dividing 150 times the torque value by the displacement in cubic inches. So 190 in this area is reasonably decent. It's not unusual for 200. On a highly efficient, very powerful engine, 220 is possible. Again, it's just another indicator. Once again, we have the volumetric efficiency. Exhaust temperatures is screen 4. Again, a reference column. Exhaust temperatures, not used for tuning too much. We use it to make sure that we don't have in this particular case, because it was a mechanical injection, make sure that we don't have anything going lean. This one had a lobe separation angle with the camshaft being much too small, and literally we were sucking fuel out of the intake and right into the exhaust and burning it in the exhaust instead of any place else. So this is one of the things that clued us in what was going wrong. The fluid temperatures, dyno out, this is more the dyno performance. The water comes into the engine brake, it gets heated and then sent out. You start to get alarmed when this thing gets up near 185, 190. If it gets up to the output starts to get over 200, it's a possibility of turning it to steam, and then you won't be able to control the rise of the engine RPM. Coolant output, this is the water output temperature of this engine during the pull. Oil in, oil out is used for in and out of an oil cooler, which wasn't used. Oil sump temperature, again, that temperature probe wasn't used. Fuel temperature wasn't used on this one. It's now been added to be used on each and every on every engine. So, air and fuel flows. Summary of again, the air turbine fuel pounds per hour for turbine 1. Turbine 2 wasn't used. Fuel specific gravity. Every fuel has a different weight. And if you go to a dyno shop and they are not pulling out their hydrometer and they're not weighing the fuel, then they're taking shortcuts. Okay, there's no way to calculate the pounds of fuel per hour without knowing the weight of the fuel. Okay, and this weight changes based on the temperature of the fuel. So it's a thing to watch for. Like I said, if you don't see them pulling out the hydrometer and weighing fuel before you start doing your pulls, I don't consider it doing right. All right. Again, the air measure of turbine 1, it's possible to run 2 turbines. Okay. This is more dyno performance, the acceleration rate data. We have 2 different servos on this that controls the water brake. It's fully automated, and again, we set the engine RPM at 600 RPM per second. As you can see, it's stabilized at 400. Then we start the test, and it starts revving up and tries to maintain it as close to 600 RPM as it can to make repeatability. Air fuel channels. On this particular engine, we did not have the 8 oxygen sensors hooked up. We only used the 2 in the collector instead of the individuals for each tube, and that was only because it didn't have O2 bungs. If it had them, we would have used them, because it's a lot easier to tune, or you can see results on each individual cylinder doing its own thing. The final column over here is a blow-by, measuring the output of the coming out of the valve cover, or in this particular case, the vacuum pump. We register how much air is coming out of the engine. You can spot some other things like ring flutter and engine going bad or not sealing up correctly. The engine specs, this is put in before the start of the run. Bore, stroke, number of cylinders, and again some other, the servo output percentage, set point, not really much of a concern. It just gives you when it took the data point. You know, it may say 6,000, but it was actually taken at 5,999 RPM. Okay, and the correction factors, the atmospheric conditions, very, very important screen. This was the conditions in the dyno cell at the time of the run. The SF power mark that we use is fully automated, so I don't even enter this information in. It's done automatically through the sensors located inside the dyno room. And the first one is the STP, or the J607 correction factor. Like I said, it was 1.089, and the reason how they come up with that number is the J607 correction factor is based on a barometric pressure of 29.92 and 60 degrees of air, vapor and zero humidity. Because we have less air pressure, a higher air temperature, which is less dense, and humidity, which is water in the air, we have to, in order to correct it back, we have to multiply the observed horsepower times the correction factor to come to a standard, i.e. you take the observed horsepower, which was 468.7, multiply it by 108, and you'll come up with 518. The other is the J1347 correction factor, which is 104. This is used on, like I said, chassis dynos a lot. It is 4% lower because it uses, let me see here, it uses 29.39, just a second. The J1349 standard uses 29.23 versus the 29.92 barometric pressure, and it uses 77 degrees versus 60 degrees. And again, they use dry air, so you'll see that's the reason the 4% correction factor. As you can also see that the correction factor changed in the middle during the run. It went from 1.089 to 1.90. Like I said, it's fully automated. One of the things that changed was the humidity percentage. As the engine started its run and the fans were blowing, the air heated up just slightly, humidity changed just a little bit and went from 43.9% to 46%, which is 2.1% increase in humidity, and the air temperature changed from 89.6 to 89.7 during the run. So that necessitated the change of correction factor in the middle of the run. Anyway, if you're ever going to be at a happy dyno, this is where I've heard, and I've never seen it, that someone would enter in some incorrect data, and it would make your engine seem more powerful than it really is. Anyway, hope this helped out. If you're using the WinDyn Data Viewer and you have any questions or anything, you're free to pick up the phone and call me at any time, and we can discuss what you're looking at and what it means. All right. Hope you had a good day. Goodbye.